Okay, in this video, we're going to take a look at the relationship between the second derivative and something called concavity, or where a function is concave up or concave down. Now, before we get into that, it'll actually make a lot more sense if we make a quick sketch of the first derivative and the second derivative. So what I'm going to do here is this. On the top, here is an original graph, and what we'll do is we'll sketch the first derivative. And if you haven't done it yet, I would suggest watching the video that describes how to sketch the first derivative. And then there's another video that shows how to sketch the second derivative, but we'll do both those right here. So our plan will be to go ahead and sketch both the derivative graphs. Then we'll talk about what concave up and concave down mean. Then finally, we'll show how the second derivative, first derivative, and the original function are all tied together with increasing, decreasing, concave up, concave down, and so on. But first of all, let's do this. Let's go ahead and make a quick sketch of the first derivative graph. Now, the way we've done that before, just to kind of review the process, is wherever the original function has a maximum or a minimum, you've got a horizontal tangent right there. If you come straight down from that point, the derivative graph has to go through zero. Got a horizontal tangent right here. Come straight down from there, the derivative graph has to go through zero. Horizontal tangent right there. Come straight down from there. First derivative graph has to go through zero right there. And finally, got another horizontal tangent up here. Comes straight down from that point. First derivative graph has to go through zero right there. So what you've got is here's a minimum, local maximum, local minimum, local maximum. Now within each of these intervals, in this case, the original function is decreasing, so the derivative graph is below the x-axis. It's going to be negative. So it's going to go down something like this. It's going to be negative below the x-axis. Then in this interval here, the original function is increasing, so the first derivative will be positive. It'll be above the axis, so it'll look something like this. So it's going to be positive in here. In this interval, the original function is decreasing, so again the derivative graph will go below the x-axis, so it'll be negative in here. In this interval right here, it switches back to a positive slope where it's increasing again. So once again, it will be above the x-axis, maybe something like this, go from here up to here. It'll be positive in here. And then finally, in this interval over here, the original graph is decreasing, so the first derivative graph will go below the x-axis, maybe something like this. We'll kind of draw it going out like that. So that's going to be a quick sketch of the derivative graph. Now again, if you're not familiar with what I just did, there's a video entitled Sketching the First Derivative Graphs, and I would suggest watching that, and you'll see that it makes this pretty easy. Now, what we'll do is to sketch the second derivative graph, all you do is just pretend that the first derivative graph is the original function and repeat the process. Because all the second derivative is, it's the derivative of the first derivative. So with that, and we'll do this one in red. So now we'll do is just pretend that this black graph here is the original graph and sketch its derivative. So what we'll do is exactly the same process. Wherever you have a maximum, you've got a horizontal tangent right there. So I'll come straight down from that point. Its derivative has to go through the x-axis right here. I've got a horizontal tangent right here. I'll come straight down from that point. It's got a zero right there. Horizontal tangent right here. I'll come straight down from that point, and it's got a zero right here. And use exactly the same logic. Where the first derivative is increasing, then that means the slope of the tangent line anywhere in there is positive. So that means that the second derivative graph will be above the x-axis. It's going to be positive. So it'll come in maybe something like this. It's going to be positive in this interval. Now, in this interval right here, the black graph is decreasing. So its derivative will be below the x-axis. It'll look something like this. It's got to be negative. It'll go down like this. So it's going to be negative in here. Then in this interval right here, the black graph is increasing, so it goes back to being above the x-axis, maybe something like this, and goes back to zero. It's going to be positive in here. And then finally, the black graph is decreasing all in here, so it'll be below the x-axis, so we'll just kind of sketch it going off to like that. It's going to be below, it's going to be negative. So what happens is this gives you a quick sketch of the second derivative graph. So what we'd like to know now is how does the second derivative graph relate to the concavity of the original graph? First of all, you got to understand what the concept of something concave up or concave down is. So let's do the following. Let's go and we will just look at a couple of quick demos first, just to show you what concave up and concave down is and how do you sketch them. Okay, now first of all, what I'm going to do is this. I'm just going to draw a curve. Now suppose the curve did this. Suppose it started here and it went down like this, up, and I'm just going to freehand the whole thing. Down like this, up over here, down, up, and so on. And I'll put one more down like this. So suppose here's a curve. Now, what concavity is, there's a couple of different ways of doing these. I like to do them with a little thing that I call hairs, putting hairs on the graph. Now, the idea, a function is concave up whenever it is curving up. It's concave down whenever it's curving down. And one way you can kind of picture this, is, and again, I'll just go ahead and draw these little hairs on the graph, and it will look something like this. So at this point, this graph is concave up in here. So I'm going to put what look like little hairs on a carpet, and the hairs go this way. The graph is curving up and concave up until it gets to a certain point. And I'm going to say that point is about right here. So in this interval right here, the word that you're looking for is concave up. The graph is concave up. So it's all the hairs are pointing up. Now, somewhere right in here, and it's kind of a guess about where it is, it hits a point where it seems to switch to concave down. So now all the little hairs point to the center of curvature, and it seems to be concave down. And again, kind of a guess, but I'm going to say somewhere right about in here. And at this point, it seems to switch to concave up again. So now, if I drew the little hairs on here, they would look like this. So the graph seems to be concave up, and you go until just by eyeballing it, wherever you think the curvature seems to switch to curving down. So it looks to me like somewhere about right in this point right here, it seems to switch to concave down. So again, I'll continue to put these little hairs on here. And again, kind of eyeballing it, seems to be concave down, and I'm going to say until it gets to about right there. Then at this point, it seems to switch to concave up again. So the little hairs again point to this, what you can consider to be the center of curvature. And then somewhere along about right here, seems to switch back to concave down again. And it finishes up concave down. So what you've got is concave up, and you've also got concave down. So a graph can be concave up or concave down. And it divides it up into little intervals here. Now, this one, let's just kind of put a little CU in here. This was concave up. This interval in here is concave down. This interval here, concave up. This one is concave down. Concave up in here, and concave down in here. Now, if it helps you visualize this, sometimes you can kind of do this. Picture, if you were to extend these little hairs out, it's like they approach a central point. So you don't have to do this, but if you wanted to, you could think of it as being like this. You took each one of these things, and they don't actually wind up on a central point, but they seem to be pointing toward the center of a curvature this way. Then in this next interval, these all seem to be pointing toward a center of curvature going down like this. And they're not precisely, in other words, this one seems to go over a little bit, but the idea is that it's concave up or concave down. Then finally, you could actually do this. You could put a vertical line on here. So here is an interval, again, where it's concave up. Here is an interval where it's concave down. And then again, concave up. Concave down in this interval here. Concave up in this interval. So that's what concavity is all about. All it wants to know is the graph curving up or is the graph curving down? Now notice, let's leave the center section here. It could be doing this. It could be decreasing and concave up, or it could be increasing and concave up. Or it could be increasing and concave down, or it could be decreasing and concave down. So in this section, we're just worried about where it's concave up or concave down. So where is the graph curving up or curving down? Now what this is my way of doing it, and I just for lack of a better word, I always use the word hairs. So I'm going to put these little hairs on the graph. And you can think of it as a carpet, maybe a shag carpet, where the hairs are pointing up, or it's upside down, the hairs are pointing down. Now, to me, this always makes it clear, and most of the students that I have no trouble visualizing it like this. But there's another way of looking at it that people use called with tangent lines, so I'll show you that one, you can decide which way you like best. Okay, what we'll look at is tangent lines on this. Now what this is exactly the same thing, sort of. I'll do this one, I guess, in black. And the idea is this, I'm going to go over ahead and mark the intervals again. So I said in the last one that the tangent line, or I need to show one more thing, by the way, before I go on. Let's go back to this hair things. These have a name, and I think we'll go ahead and put them in, let's put them in black. So wherever the function changes from concave up to concave down at that point has a name, and it's called an inflection point. So an inflection point. And just to shorten it a little bit, we'll call it an IP. So an inflection point is where it changes from concave up to concave down. Or the other way, this one is also an IP. This is an inflection point. This is an inflection point, and this is an inflection point. So wherever the graph changes concavity, then you have an inflection point. So just a definition for you. So you've got concave up, concave down, and inflection points. So now, with that in mind, let's take a look at what the tangent line does. Now what we'll do is all the inflection points stay the same, but it's based on this. If you drew these, and again, I think we'll use black on this, we'll just stay with black, but the idea is this. If the graph, in this interval, it is concave up, so where the graph is concave up, if you draw a tangent line anywhere, notice what happens. The graph of that tangent line is below the function. So the graph of the tangent line is below the function. Now in this interval, where it switches to concave down, now if you draw your tangent lines, each one of your tangent lines is above the function. So it's above the function. And this all occurs at an inflection point, say right here. Now again, I'll draw it. Tangent line is above the axis. Draw this, tangent line is above the axis. Now when you get to an inflection line, let's kind of go back, we'll draw one more here. So it's concave down in here. It switches to concave up in here. And again, wherever you draw a tangent line, now all the tangent lines are below the function. And then when you hit an inflection point, they switch. Now let's real quickly look at this one. If it goes from concave up to concave down, in the concave up interval, it's below. If you find yourself concave down, the tangent line is above. But at an inflection point, if you were to draw a long tangent line here, let's suppose we drew one that did this and this. So another way to recognize an inflection point is if the graph crosses over a tangent line, then you have an inflection point. So like right here, if I were to draw a long tangent line right there, it would look like this and like this. And at an inflection point, the original graph crosses over the tangent line. So you can either try to remember these things by using tangent lines, or we'll go ahead and put the hairs on the same graph and compare them. It could look like this. So personally, I like using the little hairs, but they'll both give you exactly the same thing. But in the video that I'm going to show you, I'll stick mostly with just sketching the hairs. So I'll remove this tangent line thing here. And again, just put little hairs on the graph and it will identify intervals where the function is concave up or concave down. So we'll look at one more demo, then we'll finish up with our final graphs. Okay, so what I'd like to do on this one is just real quickly draw the intervals where this thing is concave up or concave down. So I'm going to come in here, and I think I'm going to do it in red again. So all I want to do is just identify intervals where it's concave up or concave down. So you can kind of do it just by eyeballing. In other words, I think an inflection point is going to be about right there, and maybe about right here, and so on. But sometimes it helps if you put the little hairs on there. So we'll actually go ahead and do that in this case. So what I'm going to do is, starting right here, I'll put some hairs that will go like this. So the idea is all these little hairs, it's concave up, so the hairs are pointing up. And they seem to be pointing up, and I put little perpendicular hairs on there. They seem to be pointing up until I get to about right there. So there is an inflection point. And the graph is concave up in this interval right here. Yet at this point, it seems to switch to concave down. So now draw all the hairs perpendicular to the curve, and I would say until you get to about right there. And it's kind of a guess where this is. So don't worry too much about exactly where, but it's going to be somewhere right in there. In this interval, the graph is concave down. Now it seems to switch back to concave up in here, and just go, and again, just eyeball it wherever you think it would change concavity, and I'm going to say about right there. So in this interval, it would be little interval here, it's concave up. Then it seems to hit an inflection point right here, switches back to concave down, until it gets, say, and again, kind of a guess here, I'm going to say about right there. So there is another inflection point. It's concave down in this interval. And then finally now the little hairs seem to switch to up. And just wherever you think it changes concavity, I'm going to say about right there. There is an inflection point. And it's concave up here. Now again, at any point, if it helps you, you can always sketch a horizontal or a tangent line here. So at this point, if I were to sketch a tangent line, it would look like this, and it would look like this. So there's a tangent line at that point. So an inflection point occurs where the graph seems to cross over its own tangent line. And then it switches back to concave down in this interval right here. So now you've got concave down. So it'll be CD in this interval. So all that is, this is just some practice to get you used to making a sketch of where an original graph is concave up or concave down. So if the original graph is concave down, it means that the graph is curving down. So it could be going up, but it's going up, but curving down. Then it could be going down, but curving down. So I like to think of concave up and concave down as either the graph is curving up or the graph's curving down. And you'll see some more formal definitions here in a little bit. So with that in mind, finally, let's go back and take a look now at our original graphs. Okay, so what we've got, here's the original graph. Here's the first derivative, here's the second derivative. So what I'm going to do is go ahead, and I'm going to go ahead and put, just draw exactly like I've done before. I'm going to put the little hairs on this original graph to show intervals where it's concave up. So just by looking at the graph, you can tell. So what I would have would be, it'll be concave up in through this interval here. So concave up in through here until I get to, say, about right here. Now at this point right here, I hit an inflection point. So that's going to be an IP. And notice that the graph in here is concave up. Then it switches to concave down in here. And it stays here until it gets, say, to right here. There is an inflection point. And in this interval, it's concave down. Then it switches back to concave up in this interval. And it seems to be concave up until about right here. So in this interval, here's another inflection point. And it's concave up in here. And then finally, it seems to switch to concave down, and it stays concave down the rest of the way. So the hairs are all pointing down toward a center of curvature. So it looks like this. So again, it would be concave down in this interval. Now, to show the relationship between the original graph and the second derivative, let's do this. Let's go to here, and we'll go ahead and turn this graph right here off. We'll just right? So we'll get rid of the first derivative graph. Now again, just looking at the original function and the second derivative, we'll do the following. Wherever the original function has an inflection point, if you come straight down from there, what you'll notice is that the second derivative graph goes through 0. So I think I'll do this. I'll actually start here and go down to right here. Then here's an inflection point here, and it goes down to right here. Now notice, wherever you have an inflection point, the second derivative graph goes through 0. Here's an inflection point right here, comes straight down, and the second derivative graph goes through 0. So where you have an inflection point on the original graph, second derivative graph goes through 0. So we can actually write a few things on here we'll talk about in just a second. Now notice, looking at the original graph, wherever the original graph is concave up, then the second derivative is positive. It's above the x-axis. Wherever the original graph is concave down, then the second derivative graph is negative. It's below the x-axis. And again, concave up, the second derivative is positive. Concave down, the second derivative is negative. So if you want to identify intervals where the original function is concave up or concave down, all you have to do is to find the second derivative, pick a test point, and see whether it's concave up or concave, or positive or negative. That'll tell you where it's concave up or concave down. Positive is concave up, negative is concave down. So now with that in mind, let's do a couple things here. We'll come over here and actually write down a couple of little odds and ends here on this. I think I'll go back to black on this. So let's do the following. And I'll tie these together. So this will be point number 1, and I'll put it right here. So where the original graph, and let's just look at it like this, where the original graph is concave up. So if f of x is concave up, so emphasize concave up, then looking down here, the second derivative graph is positive. So we'll put these together. So number 1 goes with number 1. That means that the second derivative graph is positive. It's above the x-axis. Now, let's take a look at the second thing. The second thing says this, where the original graph is concave down, so if the original graph, is concave down, then what must be true of the second derivative graph is that the second derivative graph, and look over here, where it's concave down, the second derivative graph is below the x-axis, it's negative. So where that one's, where the original graph's concave down, it's negative. Okay, now you can get a couple of other things on this. Let's look at the inflection points. So where you have an inflection point on the original graph, we'll call it like this, you have an inflection point on the original graph, f of x. Notice, wherever you have an inflection point on the original graph, the second derivative is equal to 0. So whenever you have an inflection point, second derivative is equal to 0. So step number 3 would be this. Anytime you have an inflection point on the original graph, that means that f prime prime, the second derivative, is equal to 0. So and we'll put a 0 and we'll put at the inflection points. 0 at the inflection points. And there's one more thing you can tell on this, and this is something actually called the second derivative test. We'll talk about this in a little bit later video. But let's look at one last thing here. Wherever you have, and I think again I'll do this in, well, we'll do it in black, just stay here. Wherever you have a minimum value on the original function, the second derivative is positive. So at a critical point, if you have a minimum, and we'll kind of put it up here as step number 4. So if you have either a maximum, we'll start with a minimum. If you have a minimum on f of x. So wherever you have a minimum on f of x right here, if you go back down, notice the second derivative is positive. So we'll put that in here as step number 4. So f prime is positive at minimum points. Now, let's take the next possibility. Suppose you had a local maximum. So here is a local maximum right here. So there is a maximum. So where the original function hits a maximum, that occurs where the second derivative is negative. So if you wanted to know if you have a maximum or a minimum at a certain point, you can look at the second derivative. If the second derivative is negative, you'll know you have a maximum there. So step number 5. Whenever you have a local maximum on f of x, that occurs where the second derivative is negative. So f prime is negative at a local maximum. So these are just some of the relationships between the original function and the second derivative. Now later on, this thing about maximums and minimums actually has a name, and it's called the second derivative test, and we'll talk about that in another video. But what the second derivative test says is this: if you've got a maximum or a minimum, let's put it this way, at a critical point, if you're not sure if it's a maximum or a minimum, you can evaluate the second derivative. If the second derivative is positive at a critical point, then you know that it's going to be a minimum. If the second derivative is negative at a critical point, then you know it's going to be a maximum. Now real quickly, let's go ahead and fill in some things right here. What's the relationship between the original function and the first derivative? And we'll kind of compare it to these right here as well. So I'm going to go ahead and put the first derivative information back on there. So here's the first derivative graph. And we'll do the following. And we can get a couple things here. Now let's take a look at this. Where the original function is concave up, and then now we'll compare it to the black graph. So where the original function is concave up is in this interval right here. So where the original function is concave up, now look at the first derivative. If the original function is concave up, the first derivative is increasing. So on step number 1 here, we can put this. So when the original function is concave up, that means that f prime must be increasing. So it's another way of determining concave up or concave down. Now, let's take a look where it's concave down. Where the original function is concave down, in this interval right here, the first derivative is decreasing. So on step number 2, if the original function is concave down, that occurs where f prime is decreasing. So just a relationship between these two. Let's take a look at the third point. Suppose you have an inflection point on the original graph. Whenever you have an inflection point on the original graph, now watch what happens, is the first derivative hits either a maximum or a minimum. So it hits a maximum right there, and it hits a minimum right there. So remember, what the first derivative is the slope of the tangent line. So another way of looking at this, anytime you have an inflection point, it's where the original graph hits its steepest slope in that interval. So since the derivative is the graph of the slope of the tangent line, it's going to hit a maximum. So we can kind of come down here and do the following on part number 3. So whenever you have an original function on, or an inflection point on the original function, you know that the first derivative graph either hits a maximum or a minimum. So that means that f prime is a maximum or a minimum. And you might also add here, it's where the original graph has the steepest slope. So at an inflection point, I think we can actually go up. Let's just go ahead and put that right in here. An original graph, and we'll do it in red just so it kind of stands out. At an inflection point, an original graph hits the steepest slope in that little interval. So the steepest slope. So it'll look like that. Okay, and I think that's going to do it for this. Okay, so what that is, that's just a brief overview of how the original function, the first derivative, and the second derivative all tie together. Now, again, I'll go ahead and turn off the first derivative graph because in this series we're mainly interested in the second derivative graph and concavity. But notice where you turn it off, the primary thing we're after here is where the original graph is concave up, second derivative is positive above the x-axis. Where the original function is concave down, second derivative is negative below. Then if you wanted to go ahead and include the first derivative information, you can put those together. So again, each one of these points ties together, and it shows you how the second derivative relates to the original function and also to the first derivative for that matter.